Yes, so hello all. So my name is Simo Särkkä, and I'm going to talk about solving ODEs, differential equations using the probabilistic approach. So it is actually one of the special cases of these constructs, but I'm going to demonstrate to you how you actually can do it using methods called Bayesian filters and smoothers. So I'm going to start by, we will recall how classical ODE solvers actually work, so how we can see them as a sequential fitting of a polynomial to a function. And then we will see how we can actually replace the polynomial with the Gaussian process regressor. And that will actually give us the general concept of ODE solvers based on, probabilistic ODE solvers which are based on Gaussian processes. And then we will go to, so we will see what's Bayesian filtering and smoothing. And then the reason for that is that, okay, so we will end up being able to solve Gaussian process regression problems of the kind which we actually encounter in ODE solving by using the state space representation and Kalman filters and smoothers. So that will be computationally very fast. So we will see how to do that. And I'm going to try to demonstrate. I have some Jupyter codes to show and then also some derivations, so let's see how the time goes. Then a couple of further directions and conclusions in the end. So let's start with the introduction. So first of all, the problem that we are solving is an ordinary differential equation, which is vector differential equation. So my x bold means vector here. By the way, there's always a problem when you combine like a couple of different fields. So in Bayesian filtering, the notation is pretty much orthogonal to Gaussian process regression and things like that. So you need to be a bit careful when interpreting my symbols. So I have a bit of overloading of symbols because I didn't change the notations altogether. But anyway, so we are solving a differential equation, which could be, you can imagine like a first order equation of linear kind. So the time differential of x is equal to some function f of x. So the solution could look like this, for example. So maybe the blue line is the actual solution. And so aim is to actually approximate the solution. So we want to find some approximation x hat such that this actual solution to this equation somehow coincides with, or the approximation coincides with the actual solution at certain points t0, t1, t2, up to tn. And so they are these points marked with these, I guess they're stars if I look at or see it, it's a bit small. And somehow, I'm trying to be a bit abstract, but not as abstract as the previous talk. But anyway, so we somehow want to evaluate the function on the right-hand side only in a finite number of points. Well, actually, they are going to be as many points as we have in the right-hand side figure. And so we can see that we could define that this x hat is a numerical solver for the ODE. Well, these are the properties that you could set up for a numerical solver. So we want to form an algorithm which somehow forms this x hat so that it's an approximate solution to this differential equation, so that it, in the sense that the solutions coincide at a finite number of time points. So how do you do this classically? So classical way is to, so I can reveal that it's based on polynomial approximations, which are related to Taylor series expansions, and how the algorithms are formed, that they try to somehow minimize the worst case error. So that was actually discussed in the previous talk as well. So there's a worst case error, and actually the Taylor's theorem. So Taylor's theorem is the series plus the error term. So the error term actually gives us a bound, is that how big the error in the worst case can be. So the polynomial approximations and Taylor theorem actually gives worst case error optimal ODE integration rules. And the reason, or not the reason, but difference to probabilistic ODE solvers, at least in my terminology, is that we replace this worst case error analysis with a probabilistic quantification of the error. I guess that corresponds to average case error analysis in a mathematical sense. But just to point out that these are not actually all the different things, so there are some interesting results on. Okay, you can see this average case. Okay, so this is a bit of optimistic statement, but there are some connections between like a Sobolev norm analysis and the average case analysis, so that they are not completely different. But at least this worst case analysis of the classical type is slightly different from the probabilistic quantification of the errors that we are going to talk about here. And so, how do you do this classically? So the classical ODE solvers are, well, polynomial fittings sequentially to the solution. In the sense that, for example, the Euler method, it approximates the function locally as linear. So what the Euler does is that, let's try to use my multimedia here, because let's see if this works. So that so if this would be the actual solution, so what the Euler does is that we somehow always approximate the solution linearly here, and then we go to the so it's like a piecewise linear approximation to the solution. I'm now purposely throwing it off the actual solution because because if we approximate the function by a piecewise linear function starting from a given point over here, so it will just go off the solution. But anyway, so Euler method is just doing that. So there's a linear approximation happening there. And then if we look at the Runge-Kutta methods, so they can actually be seen as higher order polynomial fittings. If you look at the derivation, so well, okay, so in general, if I wrote down the Taylor expansion on the solution, so it would contain the value, the first derivative, and the second derivative. So the differential equation only gives me the first derivative, because the differential equation tells us that the first derivative needs to be equal to f of x. So it gives, well, in the same sense as here. But then to be able to get the second derivative, I would need to differentiate the function, and to get even more derivatives, I would need to actually differentiate it multiple times. And in Runge-Kutta methods, that's avoided by evaluating the function at multiple points. And then when you look at the derivation, it's actually a polynomial fitting where you kind of cancel out the higher order terms, and then you have the selection of evaluation points which makes things cancel, and you have the polynomial weights over there. So it is a polynomial approximation. And well, the nice thing is that because it's a polynomial, it can be seen as a Taylor expansion, or it isn't a Taylor expansion in the end. And you can use the classical Taylor's theorem and the theory to evaluate its accuracy. So you can compute the worst case error from that theory. Okay, so how would then probabilistic numerical method work? So maybe you could replace the, well, we will be eventually replacing this approximation with the, well, Gaussian-Born regressor. Okay, so there's a figure, well, I already draw this same thing there, but well, the linear approximation just looks like this. So then polynomial can be seen to be a bit more accurate. Well, maybe it's obvious, but and this is a bit of faked figure anyway on the right, so it's not the actual Runge-Kutta approximation. It's a bit hard to form. But anyway, so with polynomials we get like a higher order convergence in the sense that that polynomial has like a higher order polynomial terms there, which then make it higher order. But they are also computationally more heavy. But then, so how do we go beyond polynomial fitting? So then we have the machine learning models. So many of the machine learning models are, they are regression models quite often. They're regression models, so they are kind of just special regression models designed to be suitable for certain high-dimensional problems. So that, for example, you have neural networks. So they are used in like a deep learning and those kinds of problems where you have a huge amount of data. But then today we have been talking about Gaussian processes, or yesterday and today. So actually Gaussian processes have the nice thing is that if you fix those hyperparameters, so you don't actually do the hyperparameter estimation, the whole inference is just those two equations which you have seen many times. So if you have a very small data set, actually the fitting or the prediction with Gaussian processes is very fast. There are two linear matrix equations. And then Gaussian processes also give error bounds, because you have the covariance, not only the mean. And the whole idea of the ODE solving using GPs is that we replace that polynomial approximation with the Gaussian process. And well, yes, so we get the better fit, and then we get the uncertainty quantification out of that. Because there are certain details that need to be solved before we actually see how it's done. And so, but that's the general idea. So then more details. So let's see how we actually did. So let's set a notation at least and recall how the Gaussian process regression works, because I had a bit of hard time to figuring out what's the notation, because X was the ODE and then X is the state of the Kalman filter and X is the input and so on. So just a warning that be careful. So my Gaussian process is going to be, well, it's function G for Gaussian. And then we can think about unknown functions for like y is equal to G of X. And then in a Gaussian process regression, what we do is that we have a certain set of training points, x, j, y, j, which are the parts, like pairs of inputs and outputs, observed from it. But because I've been overloading x too much, and we are going to think about the temporal processes, so let's call this x as t instead. So our regression problem is, let's see what it looks like, just to have a visual feeling then. So this will be the so our Gaussian processes will be functions. Well, this is like a y in that. I'm going to reuse. So these are Gaussian processes of t. I don't know if this helps to make it like this, but at least it's one more confirmation in addition to the equation that this is our notation. And so we can think that x-axis, t-axis as time, because we will actually have just one-dimensional input in the case of ODE solve. And yes, so what makes Gaussian process regression special? Well, as you already know, and we can also compare to the polynomial fitting, is that instead of having some kind of parametric form of g of t with parameters theta, we have, well, non-parametric Gaussian process where we just say that the process has certain mean and certain covariance functions. For example, famous one and a problematic one is this exponentiated quadratic or squared exponential. It's not squared exponential in mathematical sense, but this is very typical. So it just tells that, okay, so when the time points are close to each other, they are more correlated. And I guess this was also used in those Python demos that you had yesterday. And so it's actually quite easy to even derive how you do GP regression. Let's recall the way the equations come from and why we get the problem in the computational complexity. We will see that in a moment. So that I'm denoting the observed points as y. And then for now, let's assume that we don't have any observation noise at all, so that we actually measure the evaluations of the function. So these y's are really equal to y is equal to g of t. Then how you derive these equations is that because our prior is Gaussian, and so all joint evaluations of G are Gaussian by assumption. They have the covariance function which we have specified, and then actually here I have considered the case of a zero mean. So we can actually write down the joint distribution of the observed measurements and then the unknown one. So they are jointly Gaussian. And then so that we can evaluate the whole mean function and the covariance function just by evaluating the covariance function given in the previous slide, for example, at those training points and test points. And then what Gaussian process regression does is that we compute the distribution of y star given the observed y's. So that is the whole story. So that if we actually condition this by using a standard Gaussian computation rule, which you can find in, for example, matrix cookbook, so you will see that so the mean will look like this, and the variance, or more generally covariance, will look like this. And these are the classic equations in my notation. I guess this covariance is sometimes denoted as C, and sometimes with kappa, and sometimes with K, and sometimes with some other symbol, but for now it's K. And now these equations can be used for interpolating any, or extrapolating any value y star at any test point. And the same thing also works for the noisy case. So there's only one additional term which appears, so that, okay, so we assume that we have some IID noise there with zero mean and given standard deviation. And we want to somehow estimate the clean function. We want to remove the noise. But still the same assumptions, we can write down that the measurement points, which now also contain the noise part, and the unknown value of GT star, they are jointly Gaussian. And then we can compute the posterior distribution of G of T star given the observed points. And that gives these regression equations, which should match exactly what you had yesterday. So we also have this noise part. And so you can also have multivariate versions of these, and but anyway, so this is the typical form of the equations. And now this is to get like a, maybe now you will recall my G is my Gaussian process here, and Y is the measurements, and so on. So this is just to stick these symbols in your mind. Okay, so how do you then do? Well, okay, so what the inference looks like, first of all. So this is, well, this is like a nice animation. So this green is the prior. So before we have seen any measurements, so it's just like just a prior, which is with standard deviation of something like maybe square root of 2. And then we can condition on one measurement. So what happens is that this uncertainty just gets smaller, and then this mean also gets struck with the observation. And then we can condition on the second measurement, or actually join the first and second. And then the uncertainties are smaller here, and the mean gets tracked like a bit towards why it's not yet following this actual, this dashed line is the ground truth indeed. It's a sinusoidal. But now we can condition on more points, and we eventually get that this mean is kind of following the sinusoidal quite well, and then the uncertainty, because I calibrated it well, will also is very well following the, well, showing that where the actual function should be. But of course, like in reality, you cannot just use these equations, but you also need to somehow estimate or learn the hyperparameters if you want to do things properly, because we don't in general know them. But if you know them, then these two equations are enough to do the Gaussian process regression. Okay, so now we are closing to the actual ODE solutions. So we can also do derivative measurements, which is an interesting property of Gaussian processes. That's because we have that property that, so if you have that, well, let's say that our process is zero means, and the expected value of g of t, so this is kind of the definition of a covariance for a zero mean process. So let's say that that's k of t and t prime. Then it turns out that the expected value of the derivative and g of t prime, it's going to be the derivative of this k over the first parameter and then evaluated like this. And then we can actually compute this. Because, for example, so if we have this covariance function, so we can certainly differentiate this with respect to t. It's going to be give like a 1 over L squared, then t minus t prime square, not square, but actually without the square, because that's, and then times the function itself. So we can differentiate that. So just to clarify that it's known. And then also the expected value of the derivative and derivative in another point. So it's going to be the derivatives with respect to both the variables, like this. So evaluated at t and t prime. And what happens is that we can now do the same derivation as we did for the Gaussian process regression. So we can also consider derivative measurements. So that we can write down the joint distribution of like derivative of g of t and the g itself, and then condition the Gaussians. And we can actually write down the derivative observation Gaussian process regression equations as well. So they just contain some derivatives of the Gaussian processes, depending if you actually want to predict the value of the g itself or its derivative. And then we can also have like a derivative minus some function. So that will be the key thing that we will actually need in the ODE solution. So that, yes, and so we can have first derivatives and even higher order derivatives just by differentiating the kernel function here, or the covariance function. Yes, so what is the main principle of solving ODEs with Gaussian processes? So that we have an ODE like this. So it's an, I'll just copy the ODE there. It's an abstract ODE, no actual form given. And what we do is that we somehow try to form a Gaussian process which is solving the equation. And how we do is that, well, we say that this G, which is a Gaussian process, should be approximately the x of t. And then we are conditioning the Gaussian process, instead of conditioning it on the measurements like directly, like we don't have measurement of g of t, and we don't have measurement of the derivative of g of t, but we have measurement of derivative of g of t minus f of g of t, like this. It's just, I have just rewritten the ODE so that I just move that on the left-hand side. And this defines a nonlinear likelihood, or more like a constraint, that can be handled with nonlinear GP methods. It is actually quite interesting problem even without going to those filtering methods. Let's see what it actually means. So we have a Gaussian process, g of t. I'm using my notation of the GP, zero mean, some covariance function like this. And then we say that, well, I was just saying that I want this Gaussian process to solve the equation. So this was the differential equation when I just plug in the Gaussian process. But actually, I don't want, or I don't need to solve it at every continuum time point, but instead I say that this should be true at the points t is equal to tn. And then actually I also have that g of, let's say 0 is equal to some initial value. Actually, I need to have that. So what actually happens here is that I have the actual solution. Let's use, so this would be the actual solution. And somehow I'm selecting the points, and then we say that at each of these points, the Gaussian process should be constrained to have this equation true. So in this place as well, and in this place. So the way to think about it is that if I originally had, so before I condition anything, so the Gaussian process is just going freely here. But then I can, once I have conditioned the Gaussian process on all those constraints, it will be following very well my ODE solution. So what we actually aim to do is to constrain the Gaussian process on these equations. So that's what that means. So technically speaking, well, we can see a couple of ways that you can actually do it, because it will be also needed in those filtering-based methods. So that our constraint looks like, well, this, and then this is going to be true at like a tn. My notation breaks down, but tn is equal to 0. But now it's also possible to see this as a, yes, please.
Sorry, we don't see what you're writing.
Oh, that's a good point. Let's go through this again. So I was writing that, yes, so the constraint is derivative of g of t at n is like minus the f evaluated at g of tn is equal to 0. So that is the constraint. So one way to see this constraint is that, so let's make a pseudo measurement model. Let's call the measurement as Z. I might regret my choice of the letter, but let's not worry about that. So that let's say that we measure. Okay, so Z is a problematic letter because I was going to use the. Okay, let's. The next choice is the letter for the measurement model. Maybe H would be good. I'm going to regret that as well. So that let's say that. So that we measure actually this. Okay, let's write this down first. Tn. Let's say that we measure that plus some noise for now. And then let's call this as some kind of h of g. So what we actually have is that this is going to be h. So it's not like a, strictly speaking, a function of g, because there's the differentiation. It's a kind of functional, but you can think it as a function. So let's say that this is a h of g plus epsilon. And let's say that the epsilon is a Gaussian noise. So what this actually defines is that this is a measurement model of like a Zn given h of epsilon. Okay, that's not. I'm trying to map to my previous notation, and I'm failing with that a bit. So what I'm trying to get is that we have a Gaussian prior, a Gaussian process prior, 0, k, t, t prime. And then we have some measurements which are h of g, my h is that derivative of g minus f of g, plus some noise. And then what I can now do is that, well, I can make a GP regression on this model. So this is a proper model, so there's a Gaussian prior, and then a nonlinear likelihood model. So I can kind of compute the expected value of Gaussian process at any t star given Zn. And I can compute also the variance of the same thing. But now the key thing is to notice that actually if I set the variance, so let's say that I have assumed that this is 0 mean and some kind of standard deviation sigma squared, then it turns out that if I force that the z is equal to 0 and then sigma is equal to 0, then this is actually equivalent to constraining the Gaussian process on that h of g being 0, which is like a constraint. So what I'm saying is that we can reformulate the constraint as a pseudo measurement which we always measure to be 0, and then it means that this becomes a standard nonlinear measurement model Gaussian process regression problem. Well, standard and standard, but anyway, it's a nonlinear regression problem. There is I could talk this for a long time because there also exists constraint, like a you can actually solve the constraint problem as well. It's not really. That's more like a research question. Is that you could also rewrite this in terms of like a RKHS norm, and then you minimize that under the conditions of the ODE being true. But it's an interesting, there are multiple ways to approach this. But anyway, so the GP solution to the ODE is the solution to this problem. So you have a GP prior, and then you condition the GP prior to be so that ODE being true at those points. And then you have the initial point as well. Or maybe you could have a boundary points, so you condition on all of that. But then it's a bit heavy problem to solve. So that's why I have the second part of the talk going to filtering and smoothing methods. So now you might be familiar with this method, so might not. But anyway, so let's, at least for the sake of notation, see how they work. Yes, so what filtering and smoothing methods are concerned with, they are consoled with Markovian state space models. So we have a Markovian model for the dynamics. So this X is some kind of a n-dimensional. By the way, I might have reused n in some other context as well, but don't worry about that. So that it's a state which contains certain dimensions. And then there's a Markov transition model to model its dynamics. And then there's a likelihood, so that we have a vector of measurements, and then we specify the distribution of measurements given the state. And it can be seen as, well, hidden Markov model. So hidden Markov model is a bit of, in speech processing, it means those discrete state space models, but in general, it's a hidden state Markov model, but, well, probabilistic state space model is more, maybe more descriptive word. And so this is the problem setting. And, well, concrete toy example, which is not very toy example in the end, because it's actually very much related to those GP regression problems if you think hard. Well, so, for example, we have a Gaussian random wall, so the next state, so the state is just 1D variable, so the next state is the previous one plus a Gaussian random variable, and then the measurements are just the values of the X plus some noises. Then that's a special case of these Markovian models. So we have a 1D Gaussian transition model and a 1D Gaussian measurement model. And then these look like this, which is a prototype of a graph what those state or dynamic and measurement model look like, or the dynamics and measurements. So this underlying signal here, which is the xk, that's the kind of hidden process, and then we have some measurements obtained from it, which are those O for observation. And then, like in reality, typically when you model some dynamic processes, actually the signal has more dimensions than the measurements, so that there's some kind of inverse problem happening there. Or it might be that the state contains the derivatives, which is going to be that trick in the case of ODE solving, and we only measure the position of the, well, we don't measure the derivatives explicitly, but we just can infer them based on the observations of the function itself. And then we have a certain classical classes of models. So we have the Gauss-Markov model. So there are linear dynamics for this vector x. So this A is a given matrix, and then this Q is a Gaussian vector Gaussian random variable. Then the measurement in this linear Gaussian model are also linear functions of the state plus a Gaussian noise. But then the formulation itself allows for, say, nonlinearities in the dynamic model and the measurement model. Or then we might have a continuous discrete model. So instead of having that the dynamics jumping from discrete time to another one, we can actually have a continuum of the between the measurements. And the theory or methodology of that is actually very much related to, well, similar. And actually, we will need actually this class exactly if you do the ODE solutions. And so what's the point of Bayesian filtering and smoothing? So that given that we have these nice Markovian properties of the model, so given these, we could just write down a big Bayesian inference problem in principle and then solve it by Bayes' rule. The problem is that if you think about even the linear Gaussian case, so it will have that cubic computational complexity problem exactly arising. Because you will, even in the linear case, you will need to invert that kind of matrix. And then in nonlinear case, non-Gaussian case, things will only go worse. But yeah, so this could be called like a curse of computational complexity. And but then the point of filters and motors is that there are certain marginal distributions that you can actually compute in linear time with respect to the number of time points instead of the cubic one. So they are the filtering distributions which are certain kind of marginals of this full distribution. So it's actually the marginal of the last time step given the observations and also like a if you condition only on the previous observation with respect to time. And then prediction distributions, and then smoothing distributions. So the smoothing distributions are going to be interesting here because they are actually the actual marginals of this joint posterior distribution. And in the case of ODE, we will be fine with the time marginals because we don't actually need to compute like a cross dependencies between different time points, but we just want to have like a single time point solutions in the ODE solver. So the smoothing distributions will be very useful. Well, the filtering distributions as well, both of these will be related to the ODE solutions that we will have. And so this is trying to illustrate the filtering and smoothing. So this is where the measurements are. And this is where the estimate is. But let's go to see what actually is happening. So what this filter actually is. So it is actually a computational method to compute these distributions using certain kind of recursion. So we have been given a Bayesian model. So we have the prior distribution, which is actually the distribution of the initial point or initial state at time x0. It could be at x1, but I'm using x0 as the starting point. Then we have a state space model, which is defined by the Markovian transitions. So we have been given these distributions or densities of them, and then also the likelihoods or the measurement models. And then we are given a measurement sequence. And what the Bayesian filter actually is, so it is a recursion or iteration rule, so that if we know the previous marginal filtering distribution like this, then it's just a set of equations which transforms that into the corresponding filtering distribution at step or the current step. So it's a recursion from step k minus 1 to k. And it needs a constant number of operations to do this. They are like a prediction and update operations which are inside, so that it will have a computational complexity of OT. Also in the case of, well, in the linear Gaussian, but in general, yes. So what the filter actually does is that it implements these equations. So there's a prediction step, which is the Chapman-Kolmogorov equation. So this is the previous filtering distribution, so we integrate this, multiply it with the transition density and then integrate over previous state. And this gives the kind of the predicted distribution of the state. And then we use the Bayes rule to condition on the measurement, so we get the next filtering distribution. So this is the filter in its full formulation. Well, then we have the normalization constant as well here, but which might or might not be needed. And then there are, well, certain special cases, but okay, so this is illustrating what this looks like if you want to understand. So the optimal solution just, or the Bayesian solution to state inference just happens to have this kind of form. So there's a prediction step which somehow like uses the dynamics, and then it's reused as a prior to the measurement step, and then you use the Bayes rule to update, and then you again form a new prior recursively and so on. But in practice, what you see is that you will see, for example, the Kalman filter. You can find it from Wikipedia here. So this can be seen as a Bayesian filter for the linear Gaussian case, yes. So if you discuss Kalman, that's not the case. But anyway, so you can derive the Kalman filter equations as the solutions to the linear Gaussian state space model filtering solution or solution to filtering equations for that case. It's a method which is described summary here. Okay, but you can read it if you want to actually see the equation. So it's a set of linear equations in the end. So the prediction step, instead of computing the Chapman-Kolmogorov equation, you have two matrix equations there. And then for the update step, instead of having the Bayes rule, you will have a set of matrix equations which are like computing the means and covariances using these kinds of equations. And then in nonlinear case, so the classic way to go is to linearize. So you locally linearize the nonlinear function and then you apply the Kalman filter. So that should be the extended Kalman filter. And it is approximately solving the Bayesian inference problem on those Markovian models. And then you have all other kinds of methods like unscented Kalman filter is a numerical integration based. So it's Gauss-Hormite Kalman filter. And then you have particle filters, which is Monte Carlo representations. Grid, so if you can actually discretize whole state space, you can solve the equations. Well, they are just integral equations, so you approximate the integrals in a grid, and that can be sometimes used. And then mixed Gaussian approximations, like multimodal Kalman filters, Rabe-Class particle filters, and so on, exist as well. And then the smoothing problem. So how do you solve it? So the smoothing problem was that, okay, so we have the full posterior distribution, and I claimed that you can actually compute the marginals of that in OT time. And so what this looks like, so we have the state space model. Okay, so I could have put this the other way around, but anyway, there's a measurement model and the dynamic model. And then the classical solution is so that we assume that we know these filtering distributions already. And then the smoother is now a backward sweep or backward recursion, which computes these smoothing distributions, which are exactly the marginals of the full posterior distribution. And it's backwards because it turns out that actually on the final step, the filtering distribution and the smoothing distribution coincide. So then we will get these kinds of equations. So we start these from the last time step, and then we sweep these equations backwards. And so what we have here is that this is actually the same as the prediction step of the filter, and then this one is, so what we have is, so this is the smoothing distribution at the next time step. This is the dynamic model. This is the one which we compute here. And then this is the filtering distribution. So it's a quite a large integral, and then we need to have a representation for the densities. But anyway, it's kind of doable, and it's constant operations per time step, so it's a OT algorithm. I'm not sure if they actually have the linear Gaussian special case here. Yes, they seem to have. So in a linear Gaussian case, it's just reduced to like matrix equations of this kind. So we just compute mean backwards and then covariance backwards, and that's it. And then, so that was the like a Kalman smoother or Rautung-Striebel smoother, and then you can also handle nonlinear models by linearizing, so you get extended, unscented, and sigma point methods and so on. Then you can use numerical integration. Then there are iterated smoothers. Actually, the solution which we are going to have is going to be an iterated extended Kalman smoother in the end. So they are, well, there's a longer story. So they are actually like approximating the maximum a posteriori estimate of the trajectory in a certain sense. And then particle smoothers, Rabe-Class particle smoothers, so there are multiple methods in that direction. Okay, so let's then try to connect these two things together. So how to solve ODEs using those Bayesian filling and smoothing methods. So first, there's a motivation, is that it's this computational complexity which we discussed before, or like it was discussed before yesterday, I guess. So that in the equations which we derived, so we had this inversion happening there. And then whatever we do, for example, we could do Cholesky factorization or LU factorization or LDL or something like that. So all of those have complexity of n to the power 3. So it means that if we actually have an ODE solver which wants to evaluate our function with 50,000 points, we will have a small problem in computing this covariance as we saw, I guess, yesterday. So we have the same problem. So that's why we want to actually do something else. So there are those sparse and reduced rank and related approximations that have been developed for this purpose, but here we will use, well, we will reduce the regression problem into a Kalman filtering and smoothing problem. So that will be our approach. And that will have the property that it will be linear in complexity in the number of time steps. And so this approach is based on multiple different views that you can have for Gaussian processes. So what we have seen is that, well, one way to see a Gaussian process is to fix the covariance function. Oh no, I have C here, so it could be K, but anyway, so this is where the notation becomes a bit mixed. But anyway, so we can fix that the covariance function of the process is, for example, the squared exponential. So that would be how you typically implement Gaussian process regressors. But then if and when it is like some kind of isotropic covariance function, then if you take the Fourier transform of it, you will get something called spectral density. And spectral density is used a lot in signal processing. So well, in audio signals, the spectral density, it's kind of the spectrum. And but then there's also a third one. So it's in terms of sample functions. So that it turns out that actually these Gaussian processes can be constructed as solutions to random differential equations. So let's see how it's done actually. So for example, so this is an Erstein-Uhlenbeck process. This is actually quite nice analytical example to compute also. So that we can define that we have a x of t, which is actually a solution to a random differential equation like this. So the time derivative of x is equal to minus lambda, where lambda is a constant, times x of t plus w of t. And then this w of t is a white noise process, actually Gaussian white noise process with zero mean and like a Dirac delta covariance function, so they are completely uncorrelated. It turns out that this is a Gaussian process, and its mean is 0, and the covariance looks like this. And the spectral density is going to look like this. It's a nice analytical example, by the way, to just see how these relations work. So, because this might be something that you have seen in like engineering classes, because this is typical in control engineering. So that let's say that we have this differential equation like this. Now we have this depends on t, so I will just drop the t. And how to solve this? One way is to use the Fourier transform to solve it. So we can take Fourier transforms of both sides, which gives that the Fourier transform, if I have the variable of omega here, so so we have a multiple Fourier transforms. I'm going to use the right-hand side here. So this is something called non-unitary angular frequency Fourier transform, which I'm using. So you can find the properties of it on that page, and we will actually need, there will be some like a familiar looking expressions which we will need in a moment. So that, so the derivative, I'm going to denote the Fourier transform like this. So it's going to be transformed into multiplication with I omega, and then this is just the the Fourier transform, and then we will have the Fourier transform of the white noise here. But now this is just analytical, or like it's just an equation where we can actually solve for x. So x is equal to, what do I get? It's like a w divided by, it's like a I omega plus lambda. And the spectral density is actually just the absolute value squared of x. So that is the spectral density of a process. So the spectral density of this process is going to be, well, x times the conjugate of x. So the absolute value squared. And what I get, if I didn't miss any minus sign, so it should be just spectral density of white noise squared, and then there will be omega squared plus this squared. So that is what the spectral density of Ornstein-Uhlenbeck process looks like. And then actually, well, I could say that the white noise is called white because the spectral density of that is constant over frequencies. So I can just, like for notational convenience, I will say that, let's say that this spectral density of the white noise is actually given by 2 lambda. I'm going to be very clever in my choosing of the, because things will cancel. It could be something else as well. It could be any constant. But in that case, my spectral density of the Ornstein-Uhlenbeck process looks like this. So this is the connection between these two, where do I have it? Yes. So first one and the last one. So for any linear SDE, you can always compute the spectral density, well, for LTI systems. And then, so what is the covariance function of that? So the covariance function is actually given by, like it's going to be dependent on variable, which is the difference between t and t prime. So it's like a 1 over 2 pi. Then there's like integral of, oh, sorry. Yes, so I was starting to write the covariance expression. Yes, so it will be the inverse Fourier transform of this one, so it should be like x minus I omega, like this. But luckily, well, in some sense, luckily we don't need to know how to compute this, because we can go to Wikipedia page and see that, okay, so this looks a bit familiar expression, so that if the Fourier transform is this one, so then the original function should be this one. So I can actually compute my Fourier transform just by taking that result. So this will be e power 2 minus lambda omega. So that is the covariance function of the Ornstein-Uhlenbeck process. Of course, this is complete the dull way of, well, you can use symbolic computations, but there's an interesting connection to something more deep in mathematics. So if you actually want to compute Fourier transforms, you end up using the residue theorem. So if you want to compute more complicated covariance functions for certain cases, you can actually use this. So I finally managed to find a use for these things in computing the covariances. But this is a beautiful theorem, by the way. So that the use will be, well, the covariance function, yes, but actually when you need to compute the matrix exponential in certain places, actually this becomes very useful as well. But let's go back to the point. So, okay, so the zero mean property, it's actually result if you just take the expectation of both sides of the differential equation, so you will have that it gives 0. But then the covariance function can be derived in that way which we had. There are multiple different other ways to compute the covariance function of linear SDEs. But anyway, so this Fourier transform is one. And then there's one property is that so this equivalence is true because this spectral density is a polynomial, or not a polynomial, but a rational function. The longer story is that what I did here is that I was solving the differential equation by taking the Fourier transform. It transforms the differentiations to like a multiplications by polynomial or like a squares of them. We have higher order polynomials, and this always gives a spectral density which is rational. And the theorem goes the other way around as well. So only if the spectral density of the process is rational, only then there exists the path representation of the Gaussian process. So only then there exists such a differential equation which has that covariance function. But Ornstein-Uhlenbeck has it, Mattern has it, and then, well, the others you basically need to approximate. But yes, so we can now generalize this. Well, we can even, so what would be the GP regression solution for this one? So I can reveal the story lines. So that if you think about two problems, is that we have a x of, should I use g of x for my Gaussian process? I need to choose. Let's use g and recreate it maybe. So let's say that we have a zero mean with the covariance function of x minus, this would be the Ornstein-Uhlenbeck case, like this. And then I measure this at g of t n plus epsilon. This is epsilon. And then I had another way of representing the Gaussian process, which was the solution to this differential equation W, and then I could think about measuring the Gaussian process at times those Tn with this same noise. So it turns out that these representations are completely equivalent. And this latter one is a continuous discrete Kalman filtering problem. And the first one is a Gaussian process regression problem. But they are same thing. So the prior is the same Gaussian process, but represented in the lower one it's a path representation, and in the upper one it's a covariance-based representation. And that is the key thing that enables us to solve GP regression problems by using Kalman filters and smoothers. So the generalization then is, oh, I lost my slides here. Yes, so if you have this kind of Gaussian process regression problem, I seem to have a small letter k in this case, C in the previous slide and so on, but it's the same covariance still. So then it turns out that we can actually form a state-space model of this type, provided that we have these Markovian properties in a certain sense in the process or Gaussian process, so that we put like a g, its derivative was g, the second derivative was g. We didn't have these derivatives in the Ornstein-Uhlenbeck process because Ornstein-Uhlenbeck process is not differentiable, and it's a scalar Markovian process. But we can, more generally, we will have a representation so that if we stack these g's into our x vector, then this model defines a Gaussian process with the same covariance function as we have here, so that in that sense these two problems are equivalent in the sense that the posterior distribution of x in both the models are the same. And now once we have set the state estimation problem, so then there exists, we can borrow methods from signal processing. Or state estimation is that we can form an equivalent discrete time state space model. And then this is actually given by the matrix exponential of f, for example. And then the covariance of this one is given by certain integral of them. And then, well, there are two options to compute them. Either you can use the existing numerical libraries, or then you use the almighty residue theorem to compute them, so that will be just fine for them as well. And there is also a connection, so connection between these rational functions and then the covariance functions and these representations. So you might have seen something like this in control engineering courses, if you have taken those. So there is a transfer function representation, which is something like this. So they are like zeros and poles. So this is actually my Fourier transform method was using this representation. And then you have many different ways to form the state space representation. So for example, this is the canonical controllable form and observable canonical form. So this is the way that you actually proceed in forming that this matrix, for example, here. So it's a controllable canonical form of the spectral density in certain sense. And then these are the matrix exponential based solutions. And then now this is a standard discrete time Kalman filtering problem now, if you actually compare to the Wikipedia definition of well, this is a linear Gaussian state space model. And then, so what we can do is that if you have this GP regression solution, or that we want to compute the GP regression solution, then how we can do it is that we, form those matrices F, L, and H, then in certain way augment the test points to the time series. Then there's one thing we need to discretize it a bit, and then we finally run the Kalman filter forwards with the data and Kalman filter smoother backwards in the data. And then we collect the solutions from the smoother results. So this will solve the GP regression problem of the kind in O(n) or OT time. And so this is actually the same GP regression, but now with Kalman filter, so it goes forward like this, and then backward like this. And even though this is a Kalman filter and smaller, this is exactly the same solution as the GP regression solution that I had before. So how can we use this system in OD solving? And so recall that in the case of GPs, we could measure the time derivative easily. But now it turns out, as I mentioned, is that this state-based representation is often formed so that you actually have the derivatives somehow in the state anyway. And even if you don't have them, you can actually recover the derivative from the state-based representation. So the derivatives can be also handled in GP, state-based representation of GP in an easy way. So we just replaced we had H for the measurement model before here. So we just replaced that matrix with slightly different matrix. So for example, if the state contains G and the derivative of G, then typically this H matrix would be just a matrix like this. So then the derivative can be observed just by replacing that matrix with something which has 1 in a different place. So we can handle derivative measurements quite easily in these models. And now recall that I'm going to use H for the measurement of the GP itself and then C for the other one. Then what we have is that actually our constraint which we were starting from, which is so that the derivative with respect to time should be equal to f of x t, and then we can move the f to the left-hand side. So in the state-based representation, our constraint looks like this. So it's like a derivative picking matrix times the state minus f evaluated at the Gaussian process picking matrix times xn. It's equal to 0. And now I can then try again so that I'm claiming that we can also see this as a pseudo measurement model, which we tried before. I don't know how clear I was in that, but now we will actually do it. So we can write, let's say, h of n is equal to, well, this left-hand side here. And then we can make a pseudo measurement model. So let's say that the Zn is equal to h of n plus a noise. Then if we look at this carefully, is that if we actually observe Z is equal to 0, and then we also formally or practically set the variance of epsilon to 0, this is actually constraining my state to obey that constraint. So that having a state estimation problem where we have this measurement model and always constrain on Z being 0 is equivalent to constraining the state space model on the differential equation solution. And so this is the joint state space model actually. So that's the dynamics. So these dynamics are encoding the Gaussian process. Or they are representation of the Gaussian process in that state space form. And then this pseudo measurement model is this one, which is just like making the constraint into a form of a pseudo measurement model where we observe Z is equal to 0. But this is just a filtering and smoothing problem. So now we have the toolbox of filters and smoothers to use. And that's the full story actually. So this is the model form, and we indeed have a quite large amount of different filters and smoothers to solve these problems. And they indeed will correspond to different kinds of ODE solvers or probabilistic ODE solvers. So that we can use filters which provide some kind of causal estimate, so estimate of the final point only, always using the evolutions, like causal evolutions to the left. For example, we can use extended Kalman filter or unextended Kalman filter or particle filter with some modifications. So particle filters don't like the singularity of the measurement model, so that is the catch. But they can still be often used. But then iterated extended Kalman smoother can be used to compute the estimate of the whole trajectory given all the observations. So it's implicit method in that sense. Yes. So first, so what the solutions look like. So there will be the map solution, and then this extended Kalman smoother is also give an estimate of the posterior covariance. So then you can use that to estimate these covariance or quantiles over here. But I actually have a code example as well. So let's see, so this is a 2D example in the sense that we have a pendulum which is like a swinging like this, and the equation looks like this, and then we can define, this is a secondary equation, so if you define a state containing x1 and x2, so they are the alpha and its derivative, then it's a 2D system like this. And it's ODE of this kind of form, and let's see how we can actually solve it using the probabilistic ODE solver of the EKS type. So it should be here, yes. Can you see it? Well, hopefully. I can try to make it bigger. So I'm going to use NumPy and JAX to compute one derivative there, and then this stuff for plotting. And it's a good idea to use 64 bits over here. So that this would be the classical solution. So using, I'm not sure which is the, maybe this is using like Runge-Kutta method for the, so we can just call it, and it provides us as an approximate solution like this. So this is the ODE function, and then initial point, and then time, steps, length, and number of steps. So then let's see what the iterated extended Kalman smoother looks like. So the model will be like this. So first we need to form a suitable Gaussian process prior for it. We will be using integrated Wiener processes actually. I think that Philip was talking about those a bit yesterday. Not details maybe. Yes, but it's a certain kind of a Gaussian process which is quite suitable for this. You don't usually use that in regression because it's non-stationary, but it's It's often used in these OD solutions. And then our measurement model will look like this, and we will measure those z's to be or z's to be all 0 in the extended gamma smoother. So I can consider sharing this later. So if you want to take a look at, well, actually there will be an exercise as well. Am I sure? Am I right? At least for the filter part. But so what you will need to have is that first you form the state space model. So for example, the integrated Wiener process has, I have a 2D OD. I need to form like a Kronecker product of 2 parts. So that this is the like a 1D integrated Wiener process. And then I form some Kronecker products here to actually form the 2D solver. So in the end, this is just some matrix which just corresponds to the right covariance function that I have. And this is the process noise covariance which corresponds to the right covariance function. And then I will need this picking of the Gaussian process matrix and then picking of the derivative matrix. And then I'm going to compute this. This is just for trying to compute some error estimate during the iterations. And okay, so this is just an inner function for computing an error or visualization. So let's see the actual extended gamma smoother. So the ODE solver uses this measurement model. So this is the measurement model which is encoding the constraint, so that if this is 0, then we have a solution to the differential equation. And then as this is used for extended gamma filter update step, we need to have the Jacobian. But we can compute the Jacobian, for example, using JAX by using auto-diffing, or we could compute the derivative also manually if we wish to. And then we will start our extended gamma smoother from the known initial point, and then zeros for the estimate of the mean, and then covariance. I'm using 0 covariance for the initial point part, and some non-zero for the rest of the derivative part. And then extended gamma smoother is a iterative algorithm, so it has it computes the nominal trajectory, which is kind of, it's not actually the map estimate of the trajectory by using a set of iterations. And the iterations contain extended gamma filter paths, which looks like this. So we initialize by M0, P0, and then this is doing a extended gamma filter prediction step, and then extended gamma filter update step. So this is what it looks like. So it's a forward iteration, and then we get means and covariances for each time step. Then we print errors. Then we have the smoother path. So it starts from the end and actually runs that RTS type of smoother on the trajectory. And that's it, and then we update the nominal. There's a bit of trickery so that it's like a poor man's line search, which I'm using here. But anyway, so I'm actually calling this with c is equal to 1. So what it looks like is that we should get these. So these errors are not very descriptive because it's not actually printing the real minimized error. But then we will get this kind of solution. So there's nice quantiles. Of course, like this is not calibrated in any way because I'm using fixed parameters, so I can just scale the quantiles as I wish. But in reality, you would also estimate the parameters. Yes, so there's the mean solution. I'm actually using more, like a bigger delta t at least here. Yes, but this would be a solution. And the EKF-based solution, you just leave out the iteration and delete the smoother part. So that is the EKF-based solver. And then you could implement a particle filter by using a particle filter for this model. There will be some numerical trouble if you try that, but at least that would in principle work. And then one key part here is how to form these matrix A and Q, which are the state representation of the Gaussian process. So here I was using the Wiener process, but then you could So there's one catch in my example which I was using. Because you need to have the derivative in the state, so you need to have a process which is differentiable. So the Ornstein-Uhlenbeck will not work, but instead, for example, mathern 3/2 will work. That corresponds to certain kind of A and Q, capital Q, and then mathern 7/2, and many others will also work just fine. So let's see. Yes. So parameter estimation. So actually you need to tune the method. So one way to do that is to estimate the parameters. It's not going to be easy, but there are ways to do that. So there are state-based methods to estimate the parameters, yes, but they are pretty hard to use, but that's a necessary part anyway of that. And then, well, we have some research in parallel Kalman filtering methods. I guess Fatemi is going to talk about those actually tomorrow. And then what we have been lately ourselves been doing is that combine those parallel methods from filtering and smoothing context with this ODE solving in probabilistic way. And then in practice, I was using a simplified example is that, well, that works for simple models, but in reality, you need to use quite sophisticated Kalman filter and smoother methods to have a numerically stable method. So for example, you need to use square root filters and smoothers in practice. And then there is research on partial differential equation case. So the principle applies, but you will end up having very large dimensional states and so on. But anyway, it should be the same. Then the later force models, I don't know what to say about those, but they are connected. That is, you had some research on that, but yes. But then, as conclusion, so we were discussing probabilistic ODE solvers which aim to provide probabilistic uncertainty bounds for ODE solutions. And then they are based on replacing classical polynomial approximation with a Gaussian process regressor. And it turns out that, that is the main idea, but then you can also use filters and smoothers, Bayesian filters and smoothers to actually solve the Gaussian process regression equation or regression problem faster. So you need to convert that GP in the state-based form, and then you have a pseudo measurement model which encodes this differential equation. And then you can solve the state inference problem using Bayesian filter and smoother. And then you can use, for example, extended Kalman filters and iterated extended Kalman smoothers to solve those equations. And then there are some references. Okay, so maybe you have all read this first book. Then there are some PD things, and then okay. And the state estimation and filtering things are indeed our books here, so that I can recommend them. By the way, there's a new version coming in a couple of months, so you could check that. Okay, but would you have some questions at this point?